All right, thanks. Well, thanks for coming to hear a non-physicist, even worse, mathematician, talk about physics the best he can. I understand almost nothing about that equation. But I do know something about Lagrangians because I'm in optimization and optimal control, and you know, I understand the mathematics of using a Lagrangian and its symmetries and things like that. But you know, this is copied out of some book somewhere from one of the articles that I found out of this book, Universe or Multiverse. Bernard Carr, Queen Mary London, a set of essays from a conference in 2007. So I just want to tell you my sources here up front and kind of what the nature of this talk is and what the level of authority is beforehand. So first, disclaimer, you know, these are my opinions and not associated with the math and physics department of the university and all that. So as you put that disclaimer as usual, right? And also, I'm certainly very much a layman, but I'm quite interested in how mathematics is used in physics. This is really how I got into mathematics is I have a great fascination with how the beauty of mathematics can somehow give us some insight that will guide us in how to deal with matter and energy, you know? And to me that's really fascinating. I remember sitting on a floor as a youth. I had my specific gravity thing, you know, a little pretty flexible spring with my geology set, a little thing, and then, you know, you could do that and then put it in the water so you could determine something about a mineral or rocks. And so I put those things on there. I remember sitting on the floor and just watching that going up and down, saying, why does that happen? You know, what's going on there? And then somewhere in grade school, believe it or not, I came across the equation that would tell me how, if I put different masses on there and, you know, change the spring, how I could predict the period of that. And that was, I would make calculations. I would go put something. So you can see this fascination started pretty early. Well, I've been reading books over the years and listening in the news, and so there's kind of popular level books. The Grand Design, a recent one, you know, by Hawking and Mlodinow. Maybe some of you've read it, and I've read it and reread certain parts. And I was looking for, are they really going to tell me how they compute these probabilities that tells them that a parameter, there's 28 parameters that aren't shown in there at all behind the scenes for calculating that golden Lagrangian. And some of them we can measure more precisely than others. No, this is a beautiful symmetric thing, all these gauge symmetries. And it includes gravity and all these things together with the standard model. Apparently this is the best we have for getting an idea of how all these things interact. The problem is, we can't solve the Euler-Lagrange equations for that thing. A lot of the constants so there's these 28 constants, and they just have these approximate experimentally determined values. They have no particular symmetries. This is a disturbing thing apparently to physicists. And so I wanted to explore that. These probabilities that people talk about when they say these constants are sensitive. I wanted to see try to penetrate a little bit what was behind that, see if there was something behind that. So Martin Rees is a famous earlier book about this, Just 6 Numbers, about the idea of the fine-tuning of physical constants. I have to admit, a bias ever since the beginning of hearing this. From my mathematical opinion, I was just highly suspicious. One of the reasons I've kept reading is somebody must have a probability distribution here. You know, somebody must have some equations, at least a physical model that says, okay, these universes are generated in this way, or these constants are varying in this way, and then I can determine the probabilities of them. I'm still looking. This talk is about what I've found so far, okay? And so, again, my opinions, and I'd be very glad to be more informed. I would be. And so I hope, no arrogance, but maybe just hopefully humble statement of what I see right now, okay, with the knowledge I have. So I owe you to tell you about the title right up front, and this is where I'm going to end. Tegmark is a physics professor at MIT, pretty noted. He's one of the greatest enthusiasts for this multiverse idea. A particular paper I studied in this collection from this conference is written by him, and I'll come to that later if we have time. He has a multiverse hierarchy of the various models of multiverse generation. And there's four levels. So, buried in his paper there, he comes to this point. What about these probabilities? And, well, you can read it. So I'll turn to that return to that later. Well, so if enthusiast admits that, then I kind of, when I read that, I saw none of this, you know, in these books, these popular level books. But when I read that in the quasi-semi-technical literature, then I began to think, maybe I'm not just a total nut about this suspicion. Okay, so I'd like to start out just warming you up thinking about probability. I'm not going to do I thought of doing some Bayesian arguments here, which were in a lot of the papers, but I thought let's stick with basics. And so I have here 2 decks of cards. And later on I'll return to this again and make some specific calculations about this. And in here I have 2 coins. If you look very carefully, you know, I'll admit ahead of time they're doctored. But in any case, there's a couple coins. So, well, you know, people have been doing this kind of thing to make decisions for a long time, rolling the knuckle joint of a pig or something and seeing how it lands. Something that's discovered archaeologically 1600 BC in China. This is one of the original sources of original Chinese language. Is one of these things that was used for fortune telling and making decisions that nobody could seem to decide about on the basis of just straight judgment. Right? So probability's been around a long time, but scientific probability, making it clear what we meant by that word probability, is pretty young. And the same person who invented the derivative came up with this theory in correspondence with Pascal. So the Fermat and Pascal, the 17th century is a source of this more precise idea of being able to quantify probabilities and have a rational theory of this. So there's a duality of interpretations that we use whenever we apply this theory. We move back and forth, often tacitly, between the idea of frequencies of repeated events, stable frequencies of repeated events, and the strength of belief on whether we want to bet on something the next time it happens or not, or what's going to happen. So, question. You know, you've seen these kind of things, and here's a royal flush with clubs.
No.
No?
You got a spade in there. Yeah. King of spades with rest of clubs.
Let's pretend they're all clubs, all right? It's good. Thank you for pointing that out. Yeah. What's the probability I would have picked it? I'm not a card player. Yeah, okay, so let's think about this. Purely statistically. So I want you to try to suspend all your experience and understanding of cards and decks of cards. There's 52 cards in there. I counted them, and I could be wrong, but it's 52 cards in both decks there. Okay, regular decks. And here's a couple coins. So I'm going to flip this coin. What am I going to get? Does anybody know?
A quarter.
Actually 2 quarters, but anyway. So think about now. I'm going to give you one piece of information from this random process. Or in the whole day. Okay, tail. Now, what's going to happen next?
That's 2 glued together, looks like.
Yeah. So see, I should have hidden this. I mean, he's gathering information about this, right?
Got 2 heads.
Right. Okay, so here another one glued. Okay, so I'm going to flip this one. What do I get? Heads. So you have one sample of an event from this process, right, and an event from this process. Pretty similar events in some ways, apparently. What do you know? What would you predict statistically? You've got one point, data point. What would be rational to predict is going to come up the next time I flip this thing?
You only have one data point. You have to predict heads because you don't know what the other one is.
So I got tails. So you're going to predict heads?
I misunderstood that.
Oh, that one's tails, so you flip it again, we expect tails maybe.
Yeah. So you see my point. Okay, so if we don't invoke probability theory, then we've got one data point. We've got one case. Our prediction is all the other flips will be exactly the same. That's my supposition. I mean, you may feel differently about this, but now, how about this one? Tails. Okay, now that you've got two data points, what do you think is next? Well, unfortunately, maybe you're less certain than you were before with one, right? So now we begin to say, well, if you flip it a lot of times, I could get some experience here, and I could collect some information, right, about frequencies and so forth. But then I'll need, or I can analyze these systems. If I knew more about the real nature of the system of how I'm flipping here, I could be just really good at flipping too, right? Or there could be some doctoring away from your assumption about what this should be like. So think about that. What is necessary to make a scientific probability statement? What kind of things do we need to know? What kind of data would we need to collect? Okay, so I'll go through this fairly quickly. The so-called laws of nature. I got this title because I went to my son's percussion ensemble. He's a graduate student up at DU, and he played this multi-percussion piece called The So-Called Laws of Nature, and I thought it was really neat, so I put it up in the title. So the basic idea of this slide is I want to make and try to sustain a distinction here. It won't play really heavily in this, but that what we do is we work with, try to use, and we try to develop and improve laws of physics. Those are human things, they change. We know they're wrong because next year somebody will tell us, oh, this didn't work this way. We've got some huge advances, though, we've made in just this generation, to the point where the coherence, the level of coherence and faithfulness to nature has markedly improved. Not only that, but there's whole realms of phenomena we didn't even know exist, that existed before, like radio waves before Maxwell and things like that, that were predicted by theory and then detected. Higgs boson is a recent example, if that comes out to be true, right? So this is entirely remarkable. And back in the 19th century, this kind of idea of coherence, that you could even talk about a concept of a universe, a concept coherently, was not there. People trusted Kant's arguments. Kant had many antinomies, in other words, paradoxes that he stated, basically to try to humiliate thought when it tries to go too far. And he made an argument, and you'll have to read it. You could read his arguments. He has arguments for each of these theses and antitheses. And so the world has a beginning in time and is also limited as regards to space. The other one, the world has no beginning and no limits in space. He thought he had cogent, persuasive arguments for both of these theses. What's the conclusion? Humans can't think about the cosmos in a completely coherent way. We can only think about parts of the cosmos. Therefore, there is no cosmos. Because if you can't think about it, how could it be? So the scientific community respected Kant. Kant got a lot of his information about what space and time was like and how certain that was from a guy named Euler, who was the greatest natural scientist and mathematician of the 18th century. And so he took that in, and almost immediately he was contradicted by the discovery of non-Euclidean geometries. But they stuck with him. And so until very recently, and I think we should be quite astonished and happy with this actually, that we can talk about a cosmos. Well, once you can talk about one, maybe you can talk about more. This is a game that's gone way back. So the idea of a plurality of worlds, and I don't want to spend too much time on it. I mean, this has a long history way back 4,000 or 5,000 years ago in Hindu thought, in Greek thought, with cosmoi, cosmos. These people thought about that. Origin of Alexandria didn't believe in a cyclic one, but he just thought they had to be new and different. Everyone was. It's not like the coin where I flip over and over again and keep getting tails, right? That there's no reason to create another universe if it's going to be exactly the same, was his idea. But keep in mind the difference here. He's talking about a personal ground of reality, making decisions and choices for fun or profit or love or whatever. Whereas in the Hindu idea, there's this idea of an abstract process of generating universes. And in that case, it's more likely to copy the celestial repetitions in some way. So there's some deep philosophy here. But this was a very fun, popular level book. And people like to think about that. Yeah?
That's plural you have there, right?
It's plural.
Yeah.
Yeah, cosmoi. Cosmoi is played instead of cosmos. The Greeks believed in cosmos, which meant not just that there was this world, but that it had a unified sense, right? It had a unified sense of law and order. So one thing to distinguish here, though, is the ambiguity in the word world. This is post-Copernican reaction here. And world here most likely meant another planet. You know, we were discovering planetary systems and thinks about that. Pascal was, I'll quote later, you know, was starting to get frightened and in awe. What's that?
What's the Hindu view?
Oh, a Brahman day. A Brahman day is that many human years. And after the daylight portion of a Brahman day, Brahman falls asleep. He wakes up. And poof, the world goes away. And then he falls asleep and dreams the world. And then when he wakes up, the world goes away, poof. And then all the human beings have a chance to be reincarnated. And then when he dreams again, there's a cyclic thing there. And then 100 Brahman years is a Brahman lifetime. After that, he goes away, he's gone. And no more reincarnations, no more nothing. Or is that right? No more, no. Always nothing? I don't know. Okay. And so that's that many human years, trillions, right? Yeah. That's in their theory, and it's a very old, you know, thousands of year old theory. Okay, well, let's get back to modern times here. So 2000, Martin Rees, this is a popular level statement of the idea of fine-tuning and the multiverse idea. So, so there's these 6 numbers, and my concern, I don't really have time to go into it. You can read the book, but there are these numbers that are in the equations of physics, and some of them we can measure more accurately than others. Martin says, and this is just taking a part of a quote, a sentence in his book, and then the last one is a sentence later in his book. So this is page 4 and then page 164. These 6 numbers constitute a recipe for a universe. So you got the cosmoi idea there, don't you, in some way already? If it's a recipe, you could change the recipe, possibly, is the sense there. The outcome is sensitive to their values. If you move these values, you get the equations of physics will predict different evolution, different behavior, apparently. And if any one of them were to be untuned, there would be no stars. So tune suggests, you know, there's some sort of right value or good value and so forth. There would be no stars. And if there's no stars, there's not going to be any life. Maybe, I don't know, our kind of life, right? So he questions in the same, next sentence actually, just a coincidence or providence? And he says, I don't think either one. Actually, there's maybe an infinity of universes. And so there I was ready for him to say something about probability, and I didn't find it. Okay, somehow just an infinity of universes means that ours has got to happen somewhere. And then he says, well, other people say, well, we're here. So there's nothing to be surprised about that there's a universe that allows us to be here, because we are here. That's called the anthropic argument. And he says, that doesn't satisfy me. I'm still convinced that these are finely tuned, that this should be a surprise and a shock. Okay, so what's I'd like to get at, is there since there's no probability statements in these books, what's the impulse for talking about this idea of fine tuning? Is there a real, intuition here about when you see a constant, and I'm going to discuss it later in some examples, but if you see a constant and if you wiggle it a little bit, all of a sudden the system changes greatly. Does that mean something improbable has happened in the value of that constant? That's the question. And so, I've read lots of different books and articles, and I've looked and tried to think, okay, why are people making this argument? And so one thing is, I think, is to save scientific and speculative search for unity. We want to keep going in science. We want to develop these things. So we don't want to just stop and say, oh, these numbers are just that. No more to say. We want to keep exploring. So that's one motivation. And then other side, and sometimes in the same books, there's, and this was related, is to clarify and quantify our perceptions of wonder at this. Of the ideas of freedom, understanding, purpose, providence, and being itself. You know, what this impulse that, isn't it strange that things are this way, particularly this way? There's also, you read, and there's this existential sense, and you can go read these in Pensée 205. It's really beautiful writing. This is one of the models of French style in Pensée. And, you know, why is my knowledge limited? Why my stature? What reason has nature had for giving me such, for choosing this number rather than another, in the infinity of those from which there is no more reason to choose one than another? Same sentiment in some way, right? And he says up here, I'm afraid and I'm in awe that, and frightened and astonished. There's no reason to be here rather than there. Okay, let's get back to math and physics. So the question is, if you move a parameter a little bit and all of a sudden you lose something in the system, does that mean that the value of that parameter was very unlikely? That's the question I'm going to explore with this example. So what this is does everybody know what a Lagrange point? There's 5 of them around in a 3-body system. These are stable points. Okay, so Earth, Moon, there's Lagrange points here, and there's Euler points here, here, here. If of course the Moon is going around, and it could be Sun, Earth. There are equilibrium points in that system relative to a system of axes that goes from the center of mass of the 2-body system out through the rotating secondary body. So in that rotating system, there's equilibrium points. If you put like a very light spacecraft at those points, exactly, they won't move away from that relative position. So those are called the Lagrange and Euler points, or libration points in general for all of them. Okay, so what I did, I took the Lagrange points that here's Earth, here's Moon. Up here there's Lagrange point L4. And the question is, see that in our system that's stable. So if you get a spacecraft orbiting around that point, it will stay orbiting around that point if it's close enough. Okay? Now, what's the parameter here? Well, the ratio of the secondary mass, Moon mass, over Earth mass. And that could go from 0 to 1, that ratio. Okay? So we're only including going up to equal body. I mean, the other half is just going to be symmetric, right? It's going to be the other side, because then we'd switch what's the primary and what's the secondary. Okay, so here's the real axis. So what we're seeing here is, here's the real axis. So what we're seeing along here is pure imaginary eigenvalues of the dynamical system. These curves here, along these curves, pure imaginary eigenvalues, in this case, means that you can have a periodic orbit around L4 in that parameter range. Notice the peak of that parameter range, the z value here, is 0.037. Of course, there's another part up there, a mirrored part up there. Now, what are these? These are eigenvalues branching or bifurcating off, and now they have real and imaginary parts. So on one side, the real part is negative, the other side is positive. Positive real part means this is an escape orbit. Negative real part means this is a decaying orbit, decaying into the center. And so you don't have a stable periodic orbit when you're in this parameter range up here. Okay, so let's keep going with this. Notice the 0.037. Question, does a parameter sensitivity imply a low probability? Well, so the stability range is from 0 to 0.037. the parameter range, the mu range, totally is up to 0.5. So what I did, I just ignored the top part, which is symmetric part. So I'm just going from 0 to 0.5. So there's a 0.074 ratio of how big the stability range is compared to the entire mu range. Is that a probability? Okay, well, let's keep going with this. There's 166 natural moons in our solar system as far as we've been able to count so far. Every one of them has a mu relative to their primary within the stability range. So every one of them has a mu, which is less than, actually well within, less than 0.037, usually by a lot. Well, okay, so assuming independence here, let's make a little probability calculation. Then if we assume that this is a probability, not saying that it is, then what would be the chances to have all 166 moons somehow at random be in that stability range? Well, there it is, but there's only that many particles in the universe, last check, a couple sources. So if we interpret that sensitivity to the parameter as a probability, we would say we've got a complete astonishing miracle in our solar system, or I think this is the other option, which I think is it. Something makes moons small that we haven't considered yet. Like maybe tidal forces and things like that. Other things bumping into each other. I mean, there's some reason why all our moons are small around primaries possibly, right? There's other explanations, other variables that are going, other dynamics that are going on. It's the same dynamics though, right? This is all gravitational dynamics. Something else is making all the moons really small. It's apparently unlikely to have a big moon for maybe other reasons, and we could think about that, right? So there's my key example here. So let's go further here. So now I'm back to what I read, all right? And I'm trying to look for how people are explaining the fine-tuning now of the physical constants, the 6 that Reese mentions, the 28 that I'll get to later in this model. These are bright people. I mean, these are impressive people, Astronomer Royal, Hawking, and so forth. It's not just a couple of people writing popular books saying that, it's astonishing that these parameters are so finely tuned. So I want to know, what do they mean by that? It can't just be parameter sensitivity, because that doesn't imply probability by itself. You have to know more. Okay, so two sides to this apologetics. There's apologetics for theism or for design or whatever whatever kind of attack on this. And here's a statement. Isn't this statement just what I just did with my parameter sensitivity up there? Take the range that is pleasing, right? It forms what you want. And then try to see what is the possible range of that parameter, and then take a ratio. Right? I had my sensitivity range, and then I had my full range that described all reasonable possibilities there. And then you conclude, well, it's very unlikely that this universe would be just by chance, life permitting. That's the idea. The thing is, though, you find these same kind of arguments in the people who are promoting multiverse theories and so forth. The same kind of, I call it crude probability. It assumes a uniform distribution, for example. And then, so here's the other side. Luck. Well, there's probability in a way. So luck in the precise form of the physical law is not so easily explained. There's a danger in some way that this grand designer idea might come back in. And that's not the answer of modern science, Hawking and Mlodinow complain. These fine tunings can be explained by the existence of multiple universes. So there's my question. Please explain to me how this argument works. So let's go a little bit further now back to probability and talk about this. So here's the actual calculations. What do? We take a standard coin. We have a lot of experience with that. Not one of these doctored ones, This this is a two-tailed coin gluing two together, right? So what are the chances in a two-tailed coin that I'm going to get a head, by the way? Could happen, right? I could throw it really high, the glue I could break apart, and I could get two heads. It's possible. But I usually, in probability, I don't consider those possible. How about this one? Well, this is head and tail, so the chances are better to get a head. In probability, we make basic assumptions. Kind of assumption like there's really no reason I can see that one would be favored over another. And then when I experiment with it, I see that the proportion is about half. And so that's an idealization. And I did it again. Sorry about that. So let's assume all clubs. So the probability of a club royal flush can be calculated to be that the E, I guess, is a misnomer. So 3 times 10 to the minus 7th for one like that. That's really a small chance, isn't it? But if you shuffle enough cards and deal out a deck of 5 enough times, you can, well, in fact, if you do it 1,000,000 times, you have a 21% chance of having observed a royal flush in 1,000,000 5-card hands if the deck is a standard deck and well shuffled each time. Whatever that means is really hard. Many articles about it, what it means to be well shuffled. And now if you go up to 10 to the 7th, 10 million hands dealt out, shuffled, deal out, then you have a very small, 21% chance that you won't get, a royal flush out in 1,000,000 draws, and only 2 times 10 to the minus 7th chance that you won't get a royal flush in 10 million dealings of cards. So what are the chances that I would get a royal flush out of this deck here? Let's just quiz here. What's the chances that I would get a royal flush out of this deck if I kept shuffling and dealing out hands of 5 cards from the top, no bottom dealing? What are the chances of getting a royal flush? Suppose I'm going to do it, suppose I'm going to deal out 10 million hands that way. Do you think I'll see a royal flush? Yeah. And is it very likely? Yeah, according to the probability calculation. Okay. So what if I did this with this deck? And here I go. The problem is this deck, it does contain 1 joker, but I've removed all the faces and taken from that deck and put just the number cards in there to fill in to make it 52, you see. So apparently our assumptions based on no knowledge of the deck except past experience. So probability has its limitations, doesn't it? You need to know something about the deck. So if there's no faces in here, you're never going to get a face in any one of these hands, right? So we made it into something. Now this one on the other hand, there I got my queen, my jack, somebody shuffled very specially here, and did I make the same mistake? Yeah, well, I got diamonds anyway. So, you get lots of faces out of this one. And how do I shuffle, right? So what if I just, after I pulled those faces, I kind of shuffled like this, and I just didn't disturb the bottom part of the deck? The shuffling part's very important. That has to do with the distribution of the probability distribution of the process. Okay, so let's try to apply this over to the idea of a universe. I've observed one universe, but only a little part for a little while, with a little brain, little eyes. It allows life, as far as I can tell. I'm still working at it, trying to get some life. What's next? If you posit more universes, what's the other universe going to be like if I've only seen one and I know nothing about the process that generates them? One universe, it has a face. What about the next one? Will it have a face? What kind of judgment should we make based on our data? If we knew more about the process of how these were generated, we could say more, true? I mean, like those cards there and those coins. What do you need to know to say more than just the next one's going to have a face, the next one's going to have a face, or the next one's not going to have a face, it'll just be tails, just be tails, just be tails over and over again, because that's the way the process works. Okay, so summary on this point, and then I want to go into, you know, can we, from the physics literature, are people saying more about how we can calculate these probabilities, how we can justify fine-tuning? That's my idea. It's one thing just to read the popular literature, and you can't blame physics on that. I mean, a little bit, because Hawking is spokesperson. But anyway, so probability requires certitudes. If you're going to say something random, you're saying you know a lot. If you say something's random, you know a lot already. You have made a huge claim. You have to know the outcomes before you can talk about probability. You have to know anyway all probable outcomes, but how can you find out all probable outcomes if you can't talk about probability yet? It's a little bit of a vicious circle. Well, we have to have experience. So we see, why do I exclude landing on the edge? That's clearly a logical possibility, and it's clearly a physical possibility. Why do I exclude that in my probability model? Experience. I've flipped coins since I was a kid. I've never seen one land on the edge except if I was standing in mud. Okay, so you have to know the outcomes. You have to know the events. Events are collections of outcomes. These are subsets that contain outcomes. Like, for example, the universe is life permitting in the entire ensemble of the multiverse. Well, that's a collection of a bunch of universes, evidently, that have conditions amenable for the development of life. Of course, that doesn't mean life will develop. That it has its own probabilities, possibly. Okay, we have to know that those events can be collected together in a measure space, sigma, that has a sigma algebra on it to even apply these laws of probability. That's a scientific probability, not the kind that, you know, the ancient one. We have to know the proper measure function, P, that on that set of subsets of outcomes. And the probability measure has to return always a non-negative number less than or equal to 1, right? That's the measure of the chances. We have to know that the real events that we're going to apply that model to, and I've used the same letter, it really should be different, I guess, but the real event, L, like this universe popped into existence and it has life in it, or it allows life. That would be an event. It's one of those universes that allows life. That happened. We have to know that repetitions of this are frequency stable. And we have to know that the measure of that frequency stable event by the measure function actually accords with the stable proportions that we see in nature in a reasonable approximation, like that. Now, unfortunately, my movie that I made at home of frequency stable and unstable didn't work, so I can't show it to you. I used the logistic sequences and made histograms, the relative frequency histograms, so you could see this kind of. Some processes in mathematics, you form bins of the outputs, and then you can get relative frequency histogram, and it will stabilize as you collect more and more, you know, data. But then if you take stretches of 100 data points, or 500, you can see that there's some processes that are chaotic. Their frequencies, relative frequencies, never stabilize. So it's a huge assumption, randomness. It means you believe that. So here's the, let's flip back now to the, instead of parameters in coins and outcomes like that, let's go back and ask this question before I conclude and reinforce my points here and see what kind of shots you can take and questions might come up. But keep in mind this is preliminary. I mean, I'm still reading, but so the best I found in trying to tighten this idea up in physics and mathematics is this. It's a paper by a gentleman named Donahue from this big collection of papers from this conference. And there it is. Oh, here's my movie that didn't work. Oops. Okay, I guess this is coming later. I'm sorry, I got my slides out of order. I'll show you the golden Lagrangian issues a little bit later. So a few stories then. Sorry for the returning from the commercial. Here's the show again. This idea of anthropic selection says this. Okay, you got all these multiverses, but obviously we live in one that life permits life. At least we think. And so all we really need to consider is the ones that permit life. Right? We don't really need to consider all those other. So we can screen out that entire part of the sample space that include universes that don't include life. Obviously, this one includes life. So here's see if you like this kind of reasoning. 100 guns. This is due to the philosopher and scientist Leslie. 100 guns carefully aimed at your head, all fire, but all miss. Your joy, wonder, and puzzlement is rebuffed by a friend. You are clearly alive, so you just live in a universe in which all those guns missed. Are you satisfied with this explanation? This is called the inverse gambler's fallacy. I won, so I was bound to win. I pulled the slot. Somebody was sitting there for an hour, and they didn't win. I pulled the slot. It was ready. It was going to happen, right? Another issue. Tiger Woods routinely hits 6 feet from the pin on a drive, suppose. We hope. But if you watch, angles, velocities, timing, there's numerous parameters that are very tightly tuned for that to happen. And we can see that, for example, an angle would at least have a range of 5 degrees away from what he's aligning, you know, the head and this. I mean, there's 3 degrees of freedom and all that. Anyway, 6 degrees of freedom because you got velocity in each direction and so forth. So it's therefore highly improbable that Tiger Woods will hit 6 feet from the pin. Same kind of argument I gave with the Lagrange point, but a little easier, you know, to absorb immediately. No, because there's other things about a golfer. You can't just go changing these angles around and think that you wouldn't even rip the golfer's arm off or give him a broken elbow if he tried to swing a club with those parameters. So let's talk more about these multiverse proposals for trying to solve the fine-tuning problem. Well, so one thing to be said about this that's very important is that the reason for multiverse proposals is not primarily or just to solve a fine-tuning problem. Personally, I don't think there is a fine-tuning problem exactly. But anyway, not yet. But there's lots of other reasons for thinking about multiverses, and that's in cosmology we have inflation theories, M theory with 10 to the 500th possible different universes and so forth. This is coming out of multiverse theory, that there are multiple universes. Another source of this is in particle physics. People, it's hard enough for me to understand much about quantum mechanics and its solution of the hydrogen atom with one proton, but to think that you could apply this some overall histories to the world, you know, the entire universe is way beyond me at this point, and I won't have time. It would be beautiful to be able to understand what they're doing, but so there's lots of reasons in cosmology for equations and methods hypothesizing multiverses, besides trying to say that because there's a whole lot of them, that explains why the constants are so well tuned. So the only thing is, too, if you tried, it is admitted that this is probably the best answer to the fine-tuning problem that's posed, that the multiverses. There's a lot of universes, and we happen to live in one that has these constants, but there's lots of other ones that don't have those constants and don't have life or do. And it does solve the problem. I mean, if you get a royal flush on the one time, so okay, that's really amazing. But if you sit here for 10 to the 7th hands and you get a royal flush, that's not too astonishing, is it? Unless you're in this deck. Cards would wear out long before that, I'm afraid. Supporters, you might think, well, the people, you know, that think of the multiverse, they got to be people who are trying to say that there's no design argument. It's not the case. You find supporters and people that are doing theology who use the multiverse idea in their thoughts. So I found it was interesting. It didn't divide this way in terms of people who were willing to have this idea. And it was repeatedly called in these articles extremely hypothetical with no natural or specific probability spaces or distributions. So this kind of tentatively answered my question as to whether people have real probability arguments to say that the generation of multiverses will answer some fine-tuning problem. Okay, now, another thing more tied back to the golden Lagrangian as advertised in the previous commercial break. So, the standard model is beautiful, full of symmetries. It's amazing that you can write down all these terms. To solve it for even the most kind of basic structures and geometries in cosmology, it requires something called perturbation theory, where you make expansions. In those expansions, there's coupling constants come in the way that you make the expansions. And you only expand a few terms and so forth. Well, so there's 28 constants that comes in there. None are predicted by the theory. None are organized by the theory. The empirical values obey no known patterns. They're seemingly random parameters. And this, according to the author, reinforces the feeling that we need to understand more about this model and how it relates to the universe. 3 of these 28 are claimed by various authors to be particularly puzzling because they're unnaturally small. Now we're getting somewhere. What does it mean for a parameter variation to be small, or a parameter to be small relative to what, right? What's the size? What variation should we expect here? So here's the one, the cosmological constant. This is the new in 1997 data, and inference from it suggests the universe is expanding faster than we think, or expanding. And theta and the Higgs expectation parameter. So what's this naturalness and fine-tuning? So this author explains that there's 2 kinds of fine-tuning. There's the one that's well-defined in particle physics and has a specific meaning. And then there's the anthropic fine-tuning that is discussed in the literature. Here I was on to something. I was happy. I'm going to get somewhere. So not much time nor understanding to go into this, but I'll loan you the article. It has to do with when you make these perturbation expansions, there's a quantum correction that goes in. And if that quantum correction is greater than or equal to the parameter, the total value of the parameter that's measured in experiments or observations, then they'll call that unnatural. Okay? And then they'll call that fine-tuned, because it's not, it shouldn't be that way somehow. But this author admits there's no technical fixes in sight, and the multiverse idea would not explain these fine-tuning phenomenon. They might explain some of the others, the other 28. Okay, so Tegmark, let's back to him, the guy who was embarrassed. He's classified models. There's the infinite ergodic model, and that's based on chaotic inflation. There's no fine-tuning solution there, including the multiverse. There's inflation with spontaneous symmetry breaking. And that kind of universe generation would have different laws and parameters for each one. The other one is just based on different initial conditions. Many worlds exist simultaneously. The only problem is this is in Hilbert space. It's not in real space. But who cares, right? Because what's another space in another universe? I don't know what that is. Those people know what that is if they're there, and not if they're in that deck. Okay, and then here's the wildest one that Tegmark is selling. Anything that's mathematically conceivable exists in physical reality. That would make a lot of universes, if we could think of them. Okay, well, so back to kind of a conclude here. Tegmark says in his paper classifying these attempts to model universe generation in a multiverse that, wow, the more and more we talk about this, the more and more it's embarrassing that we don't have much to say about a real probability calculation. I'd like to end by saying something positive. This has been my whipping boy all the time, right? So I want to try to quote somebody here. The best book I found to kind of discuss and give a history of it not as technical as this one I'm referring to, you know, from the conferences, is Michael Heller's Ultimate Explanations of the Universe. And I picked this up thinking, you know, he was going to be more critical than he was. He's quite positive about multiverse and ideas. And it's a kind of historical approach, and then it bends more toward the philosophical at the end and so forth. And then he gives a little critique at each one, shows how various attempts have failed, and what's current. And so this is taken, and he's got numerous places in here where he praises this. So here's what he has that's good to say about the in defense of scientists considering multiverses. He looks back at the history of science and he says, look, the way science works, there's always a rim of speculation that goes on. That's why we get new ideas, you know, if we're just always in the same rut. So if we cut all that off, we would probably be killing the goose that lays the golden egg. But he comes down to and you can read it, you know, I hope you do. So he comes down to the end. Yeah, well, you know, the multiverse idea is doing this for us now. And it could do so even better if it was combined with some rational criticism. Okay, so, and then, you know, if you want to see, he's got other comments about probability use and things like that. I would highly recommend the book if you're interested in this. So let me conclude here. So in conclusion, here's my points if you didn't get them already. Or if they were incoherent. They'll probably be incoherent again. Probability presumes possibilities. The mere randomness can't create or explain, but it can only explore the potentials of being. Now, I know many philosophers disagree with me on this. I don't see how to avoid that. If you're going to talk about probability, you have to know something can happen. How can you assign a probability to something that you don't even know could happen? And we don't know the possible until it happens, really. Probability presumes also fixed frequencies in repeated events. There's plenty of phenomena that are chaotic. They don't obey fixed frequencies. If you bin up the data of stretches of any arbitrary length as it's coming out of this process, and you make histograms, relative frequency, they just thrash around like this. They never stabilize into fixed proportions. Thankfully, there's some of them that do, including people's behavior. But that doesn't explain me, does it? I have not met, I don't know what this is talking about, speaking of incoherence, some kind of a typo here. This is not met for fine-tuning and multiverse proposals. Nowhere in my reading, and again, this is a preliminary report, there's a whole lot of literature. I know almost nothing about this and I'm talking, but I'd like to learn more. Inform me. Science requires commitment to action. Here's my final thing, going off of Heller's thing. I think the multiverse exploration, as long as it doesn't take too many of my tax dollars, is a wonderful thing. And it's probably in the main good for physics if we can talk about it and have rational criticism. And so we need to realize that science requires a huge commitment to learning and action, a lifetime of investment. You can't do that with certainty. I didn't know how beautiful mathematics was going to be and how useful and how much money I could make with it when I was 5 or 10 or even 22 and as an undergraduate. I decided on something. Our hints, our hopes, our speculations, our wonders, not just our rational criticism and skepticism. We got to have them both. You know, we got to have them both working together, and usually that means you and me, right? You criticizing me and so forth. There's a slogan floating around. I've pondered it. It convinced me the first time, but the more I read, the more I think, the less I think of it. Extraordinary claims demand extraordinary evidence. I think that's false to the history of science and the practice of science. I'm not saying that when we declare science law, we don't apply that. Well, do we though? But anyway, I mean, to a certain degree, I'm saying that in the whole sweep of discovery and living, we can't live that way. Hey, thank you very much for coming and hearing the talk.
You didn't mention anything about falsifiability. I think that is one of the, say, deeply troubling things about multiverses and so forth.
Yeah, I had a slide in there like that. I had to cut back, and then I just thought of my conclusion there and decided not to touch that. But I agree with you. If you can't observe something ever, then and so how you call it science, but so it's some sort of around the aura of science, and whether it's good or bad, I think depends on the situation, doesn't it? And what? Yeah, that's a tough one.
Yeah, and another question, we're running out of time here. Bruce, I would agree with you, but I'd like to hear your reasons for saying you don't have a problem with fine-tuning.
Oh. Okay, so I don't have a problem with pursuing the idea. Right now I see absolutely no justification in the idea of fine-tuning. So, you know, keep in mind I'm a mathematician, and I work with all kinds of mathematical models. In particular, I'm in optimization. And when you optimize a system, which are physical law, you know, principle of least actions based on Lagrangians, all that, based on optimizing, right? When you optimize a system, it's very frequent that you force it into a very particular and unusual situation. Sometimes because of constraints, you get it down into a corner. If you wiggle a little bit, the system behavior goes away. So I see this so often that I'm maybe jaded by this, right? That just because a parameter is wiggled what seems to be a very small amount, even if it's dimensionless, right? So I mean, there's that problem too. What units? I mean, what's Michael Jordan's height compared to a light year? You know, if he would vary just a very small fraction of a light year, he wouldn't be able to play basketball. Okay, well. But even in dimensionless units, and so parameter sensitivity does not imply probability. So what does fine-tuning mean then?
Yeah, well, let's say I'm thinking about, you know, the existence of, say, life in this universe. If we change a few of the parameters, you know, would there be no life, or would there be other forms of life?
So my question is, why would I even think that there be a universe? I mean, these physical constants are part of the laws of physics, are they not? These laws of physics have been, by observational data, we have measured these parameters to the degree we have. Why aren't they just inherent in that set of laws of physics? If I go to if there was another universe, first of all, why would I think the same equations would be? You know, I mean, they're talking about wiggling parameters only in the same equations, mainly, not always. Now, if you let me take any old kinds of equations, now I've got a set so huge that set theory says you can't even talk about a set like that. That's too big. I don't know if you know about this, right? Bertrand Russell's paradox. You cannot talk about the set of all possibilities rationally. So I guess that's my, I don't know if I'm catching with, you know, what, I just don't think it makes a universe. I don't see any reason to why another one would make another universe.
If we tweak the values of some of the fundamental constants in this universe,
yeah.
I think there could maybe there would not be any life whatsoever.
Yeah, but then there might not be a universe at all either, right?
I don't know.
Well, that's exactly it. Yeah, I don't know.
About the big
The only universe I know about is this one. It's got that set of parameters. And I don't know anything about a probability distribution. You see, that's another problem. What is, if there really is a set of universes, then what's the distribution of the parameter set over that entire ensemble? Is it uniform?
Yeah.
Or does it really highly peaked around these parameter values?
Yeah, as your examples show here, with a sample of one, which is all we have in terms of cosmology,
yeah.
What can we say? We can't step outside of it all and look at all of the possibilities. So sometimes I wonder, really, whether cosmology really can even be considered a science, to tell you the truth. You know,
yeah, you wonder if it...
Here, I think, you know, works really well for most sciences, but not maybe for cosmology. And I think that was quoted many, many times by Carl Sagan.
Yeah.
He used to say that about UFOs
yeah.
and things like that.
Yeah.
But whether or not that would apply to the big picture, the cosmological picture, I don't know.
Yeah, I just wondered how certain Columbus was that when he took this extraordinary voyage. And where would we be if he hadn't? That's kind of the thing I'm thinking about. You know, I'm talking about action.
Yeah.
And once you're sitting in an armchair and you got it all figured out and you just stare at the world and you don't care if you're old, you know, I can see making this kind of statement. But if somebody tells you down the road there's free hamburgers and you're 17 and you're hungry, you're going to walk 5 miles, whether it's, you know, a lark or not. That's the way my life was. It's getting less so because I'm more secure. But yeah, but no, I mean, that's my opinion is, and I don't know. I know a lot less than these people, which makes me really suspicious of myself. So that's why I wanted to read more, and that's why I thought it was a great opportunity. I didn't plan on giving this talk, but Marta, because I've been working on this, and I thought maybe another year or two I'd be ready, but I figured I could get some correction and re-steer. Yeah, well, we should talk more about it.
Yeah, it's good.
Yeah.
Yeah, you can always.
Yeah, I don't know, was this helpful at all? I mean, I'm totally off track, or do you think I should keep going developing this kind of thing, or it's a waste of time because it's a crackpot idea? Anyway, I mean, this is, or mine.
Well, I think it's an important thing to talk about this, probabilities and so forth, because there's a bunch of people who are evidently a little, let's say, unhinged.
Yeah, yeah. Or want something too much, maybe.
Yeah.
Whatever, yeah.
One comment that I frequently make is that physics is applied mathematics the same way a car is applied wrenches.
Yeah, right. It's not the purpose of it.
Yeah,
Yeah, right.
They're playing as if mathematics is controlled.
Yeah, and you know, the thing is, if you read the history of mathematics, you see it's often just the opposite. Not always, but remarkably sometimes not, but it's often just the opposite. People developed this mathematics to describe nature, a particular part of nature. That's why so they observed the phenomenon, they thought about it, and abstracted, and then they developed, of course, well, then it fits, right? I mean, but it's still an amazing thing that human beings could use language like that to make decisions about what to do in the world, I think. Question?
Yeah, you're saying that the whole set of every possibility ever that could happen to make universes, what if you were to like construct or make that smaller to a finite set of all the possibilities from that equation, but instead of like an infinite every single possibility, like make it a smaller range?
Yeah. Yeah, if you have a finite set, there's no problem forming subsets and so forth, if it's well defined.
Right, so could you do that with the equations that we have and then see which ones are probable?
Well, okay, so the equations we have, first of all, this is kind of a quasi-pretend poem. I mean, like we say, we know the theory of the strong force, but really we got a whole family of theories, right? Electroweak, we've got pretty good and we can predict, but the strong force, people say we've solved that problem, but actually we haven't, I think. Am I right? I mean, there's a multiple of possibilities and we think we kind of have it right, but we haven't got there yet. It's a lot of pieces to put together. And then how relativistic gravity fits in with the quantum theory, it's highly questionable, right? So here you can write down this golden Lagrangian, but so that's the first point. That's quite hypothetical as a point, right? And then second point is, that's for our universe. So if you go wiggle the parameters and then claim, now you've got another universe. That's to my mind, to posit some sort of being to mathematics that is not what it is. Mathematics, to my mind, is in my mind. And then I write down on paper so I can go to other people's minds and they can correct me and think about it, right? I don't go with Tegmark, who says anything mathematically possible must exist physically in reality.
You want to know my test?
Yeah, right. Well, yeah, we should let people pass out. But man, thanks for your feedback, and you know that anonymous notes of criticism under the door will also work, and this, you know, I'd be glad for the steerage.